how those can be exploited, etc. So, let us discuss on the structure of polymers, their properties, and relation of these structures with the properties, how these are related. There are few points. We will go through these points when we shall discuss the structure of the polymers and their properties. The molecular weight comes first, then we would be able to know what is the size of the polymer molecule. Is it monodispersed polymer, means the sample of polymers, whether it is having uniform molecular size, uniform molecular weight or not, or that is a mixture of many different polymer species having different molecular weight. Accordingly, we can expect a distribution of molecular sizes in the mass. If that be the case, then how the properties of such type of polymers are influenced by such molecular weight distributions. Not only the properties of the polymer during service or during use, but how these polymers behave during the processing and fabrication of any polymer product. So, there this molecular weight and molecular weight distribution, molecular size distribution has profound role to play. Then comes the linearity and non-linearity of polymer chains. What happens if a polymer chain is linear? Linear, you know what I mean to say linear, means a line like, thread like. Say, think of a bamboo having branches. Bamboo is the longest grass, bamboo is a longest grass species. Now, we think of a bamboo having branches. Now, if you trim the branches, what will happen? It will look like a rod or thread type of thing, depending on the diameter. So, that is a linear. Now, if the branches are there, it is not considered as linear, but rather it is as branched structure. Okay. Now, if many bamboos are tied together, with the help of rope, then it is a kind of inter bamboo linked system with the help of ropes, threads. So, that represent a cross linked 3-dimensional network system. So, linearity and non-linearity of polymer chains actually influence the properties of a polymer system. Do you understand? Properties of a polymer system, how the properties can be properties of those polymers be available, and in which way they influence their behavior, linear polymer or branched polymer or your cross-linked polymer. For example, take the simple example of polyethylene. Polyethylene. Take the simple example of polyethylene. How many different grades are there? As I mentioned, LDPE. Let us take these two grades, low density and high density, HDPE. Now, this is a linear polymer, this is a branched polymer. Now, density becomes low due to the presence of short branches or long branches. So, density is controlled, density of a polymer is controlled or influenced by the presence of branches. If there are no branches, there will be compaction. So, density will be more. density of a compact system is more, bulk density of a compact system is more. So, this LDP is branched one, so it is low density, and HDP is linear, so it is high density. Think of polypropylene PP, it is the lightest polymer, it is the lightest polymer, density sometimes it is 0.09 to 0.91 or 0.92. This is the density or specific gravity of this polypropylene. Why? Methyl group is there, this methyl group and some short branch is also produced. So, that makes this polymer providing lowest density, lightest polymer, although strong, although very strong polymer. Then next point to be considered is molar cohesion. What do you mean by molar cohesion? Very simple phenomena, very simple phenomena. Try to follow this this phenomenon in a simplest fashion, you will understand. You think of a solid, say ice, think of ice, it is solid at certain temperature and pressure. Okay. Once the temperature is increased, ice starts melting, that means the kinetic energy of the water molecules are increased by increasing the temperature, all right. Now, that will continue till the entire mass of ice melts at that temperature, and temperature remains same if the pressure is kept constant. Then the temperature of the liquid water gradually increases till it reaches its boiling temperature, say 100 degree Celsius at atmospheric pressure. Then the kinetic energy of the water molecules further increases and becomes it gets converted to vapor, gas, all right. So, at that temperature, water molecules, same water molecules remains in a solid cohesion, then it remains in liquid phase, then it remains in vapor phase. So, what is this cohesion? The forces surrounding each molecule, that interact with its surrounding molecule and helps in association of those molecules in a solid state and liquid state. Even a methane gas can be liquefied and solidified. Carbon dioxide can also be liquefied and solidified. Here the cohesive force acts to play. I gave you a very good example of this ethylene gas, which is ethylene, which is a gas at ambient conditions of temperature and pressure. Now, when this ethylene is converted to polymer, polyethylene, this polyethylene again at the same ambience of temperature and pressure, it becomes solid and strong. Just compare between ethylene and polyethylene. When it is converted to polymer, it becomes strong and tough. It can bear load, whereas this ethylene gas cannot bear load. It is a gas, it is a fluid, but this polyethylene is not. How it happens? That happens due to the molar cohesion, molecular cohesion, due to intermolecular forces of interactions. Where from this intermolecular forces of interaction comes into play? There is no polar bonds, it is non-polar bond, but this is due to London dispersion force. What is the genesis of this London dispersion force? You think of this carbon-carbon bond. In polyethylene, bonds present are carbon and carbon and carbon and hydrogen. Both are covalent bonds. Both are covalent bonds. But there is a difference in electronegativity or electropositivity between carbon and hydrogen, because these two elements are not placed at the same position in the periodic table. So, there is a gap between the placement, the positions of these two elements. That is why some polarity is there. As a result of that, what happens? It actually provide some induction force, induction effect over the bonds. So, that is called dispersion force. And when it is present in a polymer, that is, take a sum of this total inductive force or dispersion force surrounding each carbon-carbon and carbon-hydrogen bonds, the total quantity of force will be enormous. So, that makes it viscous, that makes it stronger, right. So, that is called molar cohesion. You cannot forget, you cannot ignore this molar cohesion in polymer. While dealing with polymer, you have to consider this molar cohesion. Again, if you want to dissolve this polyethylene in a solvent, you take water, put polyethylene in water, does it dissolve there? No. What is the reason behind that thing? You think of, very simple. Dissolution, what is the dissolution process? When you add a solute in a solvent, what happens? Solvent provides the solvation energy, that solvation energy breaks these molar cohesive forces, cohesive bonds present in solid. Once it breaks these molar cohesive forces in solid, then it helps moving apart from each other. That means the role of solvent is to break these cohesive forces between intermolecular cohesive forces. It should break, then only individual species, individual molecules can separate each other, can move away from each other. Okay. Here is the solvation energy of that thing. Now, this water molecules cannot do this, cannot break this cohesive force present in ethylene, because it is a non-polar system. Water is a polar system, polyethylene is a non-polar system. So, you are putting a non-polar system in a polar system, it cannot break. So, it cannot dissolve, it cannot act as a solvent. Then what should you do? You should select a non-polar solvent. What are those non-polar solvents? Could you give me example of non-polar solvent? THF, who told THF? Who told? Who told THF? Why you said THF? Is that a non-polar solvent? THF? These are fundamentals. These are fundamentals. You always ignore these fundamentals. If you do not know these fundamentals, you won't understand this subject. THF is not a non-polar solvent, it is a polar solvent. Dimethyl formamide is a polar solvent. Alcohols, say ethanol, methanols are polar solvents. Benzene is polar solvent? Benzene is non-polar solvent because it is hydrocarbon. So, you have to take a hydrocarbon solvent. You take benzene or toluene or xylene, hexane, heptane, aliphatic or aromatic compounds, aromatic or aliphatic solvents. So, you take this polyethylene, put in heptane, it will not dissolve, although it is non-polar. You put in benzene, no, it will not dissolve. You put in toluene, no, again not. You put in xylene, no, it will not go. There are certain reasons. Try to find out the reasons. Although by theory, as I told, it is supposed to be a good solvent for polyethylene, this benzene, toluene, xylene. Yes, it is so. It is supposed to go into solution, but it cannot. Then what is done? You have to heat the system. You put polyethylene in toluene, say LDP in toluene, and raise the temperature of that toluene till its boiling point. Once it starts boiling, what is the boiling point of toluene? It is 109 or 110 degrees Celsius temperature, boiling point of toluene. So, when it starts boiling, polyethylene starts going into solution. There are reasons because these polyethylenes are crystalline in nature, semi crystalline polymer. Okay. Now, those crystallites are to be broken by that thermal energy. Once these crystallites are broken, then only these toluene molecules can penetrate in between the polyethylene molecules, and it can separate these molecules from each other by placing solvent molecules in between the solvents. Are you getting the concept? Okay. Then you cool, once again you cool that system, polyethylene will precipitate out, will come out of phase, soluble phase. Polyethylene will come out of soluble phase, solution phase. It will solidify. That is one exceptional cases, but the normal thing is, if you add some you put this polymer in a suitable solvent, then it goes into solution. I mean to say that concept of like dissolves like. Similar things. If you want to live in a room, you have a selectivity for your partner, don't you have? Can you allow anybody to live with you in your room? Are you answer me? No, that is right. Otherwise, you are compatible to that extent that you can allow anybody. Even you can live with poisonous snakes, or even you can live with tigers. Okay. Those are exceptional cases. Yes, there are persons who live with tigers. I have seen in the news that there are people who live with poisonous snakes also. Those are exceptional cases. Other than it is not. You have a selectivity to select your partner. Here also this solubility concept or miscibility concept phenomena comes from this this theory. Okay. And then I am giving you another example. You take some nylon, put in water. Water is a polar solvent, nylon is also a polar material. Can it be a solvent for nylon? No. There are certain regions. You have to find out the region. You take a dilute solution of hydrochloric acid, aqueous solution of hydrochloric acid. Put nylon, immediately it goes into solution. Probably few of you can have some experience in the laboratory. Of course, if you have done your lab classes in a serious way, then you could have noticed it, otherwise not. That is, the brushes you use with nylon bristles for cleaning glasswares. Nylon bristles, brushes containing nylon bristles for cleaning glasswares. Sometimes you use that with acids. That means your glassware is dirty, you put some acid and then you want to rub also with the help of a brush, and eventually you find it becomes just sticky and it goes away, or this entire brush is damaged. That is due to the solubility of nylon in that acid. So, sometimes acid is a solvent for some polymer. Nylon is a polymer, there is a polyamide, CONH functional group is there. Now, that CONH functional group is attacked by this acid, because the intermolecular forces of interaction in nylon occurs through the hydrogen bonding between CO and NH. CO, NH of one polymer with the other polymer. I will show. So, these are the things, solubility concept and the polar mechanical properties. So, all these things are related to this molar cohesion, polarity as well as the crystallinity. So, I have explained with the help of simple examples how this molar cohesion, how this crystallinity, how this polarity comes into play in the attack of solvents to those polymers or their mechanical properties, etc. This crystallinity also adds on to the mechanical properties. Amorphous character also another kind of mechanical properties, because elastomers are amorphous, rubbers are amorphous, whereas polyethylene and other solid plastics, they are crystalline. Then effect of temperature, how it behaves if the temperature is increased, if the temperature is decreased, because you have seen in the winter your cycle seat cover becomes hard. I do not know whether you have noticed it or not. If you take some bags made of PVC, it becomes hard in winter, and in hot summer, or if it is exposed to sun, direct sunlight, your seat cover of your vehicle becomes very soft. Why it is so? At low temperature it behaves like stiff and rigid structure, whereas at elevated temperature it becomes flexible. That means effect of temperature is also there, and again there is a limit of temperature above which, beyond which it becomes unstable, it degrades, starts degradation or decomposes, or it can be flexible. Deformation behavior in the amorphous state, say deformation behavior in the amorphous state means the elastomers they are amorphous, they deform easily. That is why we can get the comfort of riding a car using elastomer tire that is flexible, that can absorb the vibration, that provide damping action. It minimize the your vibrational energy there as due to absorption of that vibrational energy. Who wants to travel in goods car? It is a goods train. In goods train, if you are asked you want to go to Delhi, or goods train is you are not getting any accommodation in this your passenger trains. Well, this empty buggy is going from here, some your goods train is going, there is enough space, you go. Would you go? No, because you won't get that kind of comfort. This is because of the vibration damping effect. Even if a train runs at a very high speed in a passenger train, that too in AC class, there is a difference between AC class and sleeper class. Traveling in AC class and sleeper class, more dampening effect is observed, is available in AC class rather than in sleeper class. Again, there is a difference between AC class in normal trains and AC class in Rajdhani, more damping effect. Okay. And again, the bogie is meant for ministers, are far and far better than the bogies are meant for the common people like us, poor people like us. So that is the dampening effect, and those dampening effects are made by spring action, which can absorb the vibration that can be available from a polymer. You will see when you will understand, or you will see read this viscoelastic nature, viscoelastic properties, with the help of mechanical models, you will see that mechanical models are a combination of springs and dashboards in series and in parallel. You will see how this damping effect is available. Polymer is a very good material for that. This polymer molecule provides that kind of thing, artificial springs. Then transitions and rubbery regions, say glass transition and melting transition, and the property demand and for polymers induced. So these are few points I will cover. We try to understand. If you want to learn polymer, you have to put attention to this chapter. Now let us come to molecular weight of polymers. And molecular weight of polymers, how to calculate, you know. For condensation polymers, molecular weight is calculated by calculating the molecular weight of the residual Molar unit into number, average or degree of polymerization plus mass of the end groups. From there you can calculate the molecular weight. Similarly, for addition chain polymers, if you know the molecular weight of the monomer and if you know the number of units linked in a polymer molecule known as degree of polymerization, then multiplying the monomer weight by that degree of polymerization, you can calculate this molecular weight. So, these are simple theoretical calculation how to get the molecular weight value, but how to know? We need some data. That means you have to determine the molecular weight, you have to measure the molecular weight. How to measure the molecular weight? For simple molecule, what are the techniques known to us for determination of molecular weight? So, think of sodium chloride or think of say methanol, think of benzene. How to determine the molecular weight? There are certain techniques. Now, you can say, sir, that is that necessary? If we know the structure, we know the formula, so we can calculate the molecular weight. But there must be some method, experimental methods by which one can evaluate, one can develop, one can get this molecular weight, one can measure the molecular weight. That is necessary extensively for these polymers. How to measure the molecular weight? Very difficult, very difficult, because these polymers are, again I told you, it is very complicated molecule, it is very complicated. Until and unless you cannot isolate a separate polymer molecule, how can you estimate its molecular weight? So, you have to isolate the polymer molecule. Once you isolate the polymer molecule, then you can estimate its size. Then what are these techniques? Once this molecular weight is determined, for example, say by colligative properties measurement. Can you tell me one colligative property? Decrease of freezing point, osmotic pressure, elevation of boiling point, okay, depression of freezing point. So, these are the properties of materials. These are the so these basic fundamental properties of materials are exploited in measurement of this molecular weight of these polymers. And there are other techniques also. If the molecular weight of a species increases in a solution, then the viscosity of that solution varies. More concentration, more viscous it will be. So, concentration as well as molecular size, bigger the molecular size, bigger the size of the solute, when it is dissolved in a solvent, then it will be more viscous. You understand? The viscosity of water is, you can measure the viscosity with the help of flow time. You take a thin capillary, allow this liquid or water to flow through the capillary. So, by measuring the flow time of this liquid through the capillary, we can calculate the viscosity that you have already done in your lab classes. Okay. Now, once some solute is dissolved in that liquid, the viscosity changes. So, you measure the flow time of the solution of that solute in that particular solvent. So, difference from this flow times, you can calculate the viscosity. The same concept can also be extended to this polymer here. You dissolve a polymer in a solvent. Before that, you take the flow time of the pure solvent, then you dissolve the polymer in the solvent, measure the flow time, it will differ, flow time will be more. Now, you start thinking how it takes more time to flow when some solute is dissolved over there. That means, what is the viscosity? It is resistance to flow, it hindrance to flow, it resists the flow of that liquid. If you take imaginary planes, imaginary layers in a fluid system flowing through a pipe, flowing through a tube, if you imagine infinite number of layers, the resistance offered by one layer over the other is the measure of viscosity. understand. So, if the molecular is bushy, if the molecule is bushy in nature, it will offer more resistance. If the molecular is smooth, molecular nature is smooth, viscosity will be less. So, these are the basic fundamental concepts. So, let us see. Now, this is a diagram showing distribution of molecular sizes, various distribution of molecular sizes. How this is obtained? Suppose you take a sample of material, say in our case it is polymer, it dissolve in a good solvent. I mean good solvent, I mean that it can dissolve the polymer. It is a very good solvent for the polymer. That means solubility of the polymer in that solvent is excellent at a particular temperature. Again, the solubility of that polymer in that solvent at any specific temperature depends on the friendship between the solvent and the polymer. Here both are like human entities, or both are goats or lambs, but not a goat and a tiger. So, the two units, solvent and the polymer, are friendly to each other. One likes the other. So, they have likeliness with each other. Okay. The solvent can act as a friend to that polymer, polymer can also be a friend to that solvent, then only it can be a good solvent. Why? If the force field surrounding the solute and the solvent are equivalent or close to equivalent, then only a solvent can be a very good solvent. There you are putting the polymer, that polymer samples contains molecules of different lengths. So, if you are asked to develop a distribution curve, molecular distribution curve, this axis defines the molecular weight, this axis defines the fraction. So, to develop a distribution, to draw a distribution curve, what you have to do? So, you have added this polymer to that solvent, it is dissolved. Okay. Then what you have to do? You have to fractionate it. You have to fractionate it. Means you have to separate different fractions having different molecular sizes. How to do? You can do with the help of solubility property only. Then you take a mixture of solvents where higher molecular will be insoluble, whereas lower molecular will be soluble. So, this way you choose two solvents, mix those two solvents in different proportions. This way you can have containers 1 to say 20 numbers. So, you have 20 containers. In those 20 containers or 10 containers, you take 10 containers, you take say 10 cc of one solvent, 90 cc of other solvent. Then 10 90, 20 80, 30 70, 40 60, 50 50, 40 50, 40 60, just 40 60. So, this way you can have say 10 90, 20 80, 30 70, 40 60, 50 50, and then 60, 40, 70, 30, 80, 20, 90, 10 and 100% one side, another is 100% pure solvent. This is pure solvent, this is pure solvent. That means, if you take A and B 100, 100, here B is 0, or if you write this way, A and B, here it will be 100, it will be 0, like this way, 90, 10, 80, 20, 70, 30, 60, 40, 50, 50, then 40, 60, 30, 70, 20, 80, 10, 90, 0, 100. So, we are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 containers, pure solvent and intermediate compositions. So, put a stock solution, master solution is a same quantity to certain volume of these compositions. Take 10 milliliter each everywhere. The composition is like this. Everywhere take 10 milliliter. There you add say 1 cc of that concentrated solution. You will find certain fractions of solid has come out, and you filter it, wash it by gravimetric means, you get the fractions of those solids you have got. Then you plot those fractions you have got. Then with the help of other technique, like once you have got certain quantity of one fraction, you measure its molecular weight by certain techniques, by some absolute techniques, and after measuring the molecular weight, you have a data of fractions, different fractions, say 11 fractions or 10 fractions of different molecular weight, 11 fractions of different molecular weight, and then you make a plot, and after plotting you can get either this type of distribution curve or this type of distribution curve or this type of distribution curve. Now, this curve can be designated as a broad distribution curve. Distribution is broad, means it is having, this distribution shows species or portions or fractions of low molecular weight along with very high molecular weight, of which a middle fraction or some fraction, highest fraction is obtained for medium molecular weight. So, it is a mixture of low molecular weight with high molecular weight and medium molecular weight. So, distribution is broad. Now, this distribution is narrow, or it can be further narrow. It can be further narrow if this distribution looks like this. You can say this distribution is monodispersed distribution, means it contains this up to this fraction, it contains only molecules of this size. This distribution is very narrow. This is known as a monodispersed specimen. Whereas, if it gives you distribution like this, this distribution is broad. This distribution can be anything depending on the method of manufacture, etc. Now, here you have seen one curve is there which looks like this distribution, it is a bimodal distribution. That means certain your portion, certain fraction has this molecular weight and certain other fraction has this molecular weight. That means it is a mixture of equal amount of low molecular weight with the high molecular weight polymer. So, that has profound effect on the processing and fabrication of the polymer. The melt viscosity, melt behaviors, solution behaviors, all those properties are controlled by this thing. Now, for a film grade polymer, LDP, low density polyethylene, is a very good material for film, making film, whereas HDP is difficult to convert it to a film, whereas you can make pipes or other rigid structural items from high density polyethylene, but low density polyethylene can be used for making films. Not only that, during processing what happens, it needs heating of the polymer to increase its flow behavior, flow characteristics, for which it needs to be heated to very high temperature. Now, if the melting point of say HDP, melting temperature of HDP is 130 degrees Celsius, then the polymer needs to be heated up to say 160, 170. Then heating this polymer to that high temperature provides adequate fluidity, flow behavior of that polymer or rheology of the polymer, so that it can be extruded in the form of pipe, or it can be used for injection molding of items like chairs or buckets like this. So, that flow behavior, flow characteristics, all these things depends on the molecular weight distribution. Now, if there are small molecular fragments, fractions present in a sample of polymer along with high molecular weight sample, high molecular weight molecules contribute to the strength properties, and low molecular weight fractions contribute to the processing characteristics. So, here the portion amounts present in the lower side of low molecular weight, that adds to that contributes during processing characteristics of the polymer, whereas higher molecular fraction that contributes to the mechanical properties, thermal properties, all those properties. So, this shows there is a need of a broad distribution of polymers for certain applications, whereas there also a need of polydisperse, monodisperse polymer, means very close molecular weight, dispersity is low. We will see gradually. Now, you see this is again another distribution curve based on number counts, number of molecules of different species, ith species with their molecular weight. So, this is a distribution curve, how it can be evaluated for a polydispersed sample. Now, let us look into, because we will again come across about the molecular weight relations and their distributions. Now, let us say I am talking so much, but you are not getting how it is influencing or how it is related to the properties of these polymers. Now, this is a schematic representation here. This axis shows the increase of molecular weight increases in this direction, and this axis shows properties. Properties may be thermal properties, may be mechanical properties or other properties. Now, this kind of curve, variation of these properties with molecular weight. So, there is some minimum properties for a minimum molecular weight, then gradually this property increases with the increase in molecular weight. Beyond certain value of the molecular weight, then that increase of those properties are not very high, not very pronounced. What does it indicate? Suppose you have developed a polymer, you have synthesized a polymer, you want to use as a film or you want to use as making a molded item. Will it be that strong? Can it provide film characteristics? Can it bear huge load? So, these questions comes. So, that is related to molecular weight. What is the molecular weight of that polymer you have prepared? So, you evaluate the molecular weight. If you find that molecular weight of your polymer is only 1000, see the properties here. If the molecular weight is 10,000, property is higher than this molecular weight of 1000. If the molecular weight is 1 lakh, property is increased to this value. So, this can be little mechanically more stable, mechanically bearable polymer as compared to this one. So, it indicates there is a threshold value of molecular weight. What is this threshold value? The minimum molecular weight, so that it can be used as a polymer. It can behave like a polymer. What is this threshold value? For condensation polymer, this threshold value can be 5000 to 10,000, whereas for addition chain polymer, this threshold value can be 50,000, higher than 50,000, greater than 50,000. Look at the difference. Why is it so? Suppose you are synthesizing nylon. How nylon is synthesized? Say for example, nylon 66. Nylon 66 is made from HMDA and adipic acid. Initially, for nylon synthesis, what is done? A nylon salt is made. When these two are dissolved in a solvent, when these solutions, two solutions are mixed, immediately, eventually, it will form a salt, and that will precipitate out. So, if you mix a solution of HMDA and AA in water, when you mix these two solutions, immediately nylon salt, HMDA and adipic acid salt, hexamethylene adipamide, that is known as hexamethylene adipamide, that hexamethylene adipamide salt is insoluble in water, it precipitates out, you filter it. It has got advantage that this HMDA and AA, when they are polymerized, you see, if it is polymerized in 1:1 molar ratio, then only you will get a polymer, high molecular weight polymer, 1:1 molar ratio. Okay. Otherwise, the stoichiometric control becomes a problem in nylon synthesis, nylon 66 synthesis, because somehow by weighing you can take little difference, you can just deviate from stoichiometry during weighing, there may be certain mistake. So, it is very difficult to take this same weight. So, in order to avoid that, you dissolve these two and mix these two solutions, and salt will be precipitated out, and that salt will be formed in 1:1 molar ratio. Okay. So, this nylon salt hexamethylene adipamide when that is heated, temperature is around 270 degrees Celsius. This nylon salt melts, forming nylon 6,6. Now, this nylon salt, this is highly viscous. Nylon salt, when it is melted, it becomes viscous due to condensation to increase the molecular weight. So, you have to maintain that high temperature, otherwise the fluidity will not be there and your growth will not be adequate, high molecular weight formation will not be adequate. So, here you understand, in order to synthesize a very high molecular weight in condensation polymerization is very difficult. Similarly, synthesis of similar is the case for polyethylene terephthalate, that is also produced by melt polycondensation, because once these oligomers, higher oligomers means more than say 6,000, 7,000 molecular weight oligomers are formed, their melting point is quite high. So, you have to heat at very high temperature, then only it will polymerize, otherwise one will be liquid phase, another will be solid phase, heterogeneous phase will be there, polymer growth will not be there. So, both of these reactants should be kept in the same phase, not heterogeneous phase, rather in the homogeneous phase, and that is only possible if you carry out this polymerization at high temperature, polyethylene terephthalate and nylon. And even doing that, you cannot get very high molecular weight. For nylon it is okay, for polyethylene terephthalate it is okay, you can get few lakhs of molecular weights, but for phenol, formaldehyde and other polymers it is very difficult to get very high molecular weight. So, sometimes pre-polymers are made. These pre-polymers are of low molecular weight, then those pre-polymers are further converted to high polymers, high molecular weight polymers at later stages. So, this gives you a concept of threshold molecular weight of a polymer for getting or for making useful products out of that threshold molecular weight, molecular size polymers. Do you understand? So, it is 5 to 10,000 for condensation polymers, it is beyond 50,000 for addition chain polymers, and that is indicated from this schematic presentation, schematic curve. Yes, please.
So these properties they get saturated with the molecular weight beyond the levels.
Yeah, almost saturates. That means if you go further, say 10 to the power 7, you cannot get say tensile strength beyond this value, but it is not so rigid for each and every polymer systems. There is some exceptions. Say for example, polyethylene Hdp. What is the molecular weight of Hdp? Say it may be, of course it depends on the branching, say linear polymer. So, Hdp is molecular set suppose 10,000, it is a rigid polymer, but ultra high molecular weight polyethylene it is greater than 60 lakhs, 70 lakhs, 80 lakhs, like that. Now, this ultra high molecular weight polyethylene very strong and tough polymer, and it is used in place of metals. in substitute of metals. It is very strong polymer, and that strength comes from this high molecular weight, and it is difficult to process also. Of course, this ultra high molecular weight polymer is processed by sintering, not by conventional polymer processing techniques, polymer processing machineries. Okay. Ultra high molecular weight. So, there you see is an exceptional case, going or increasing the molecular weight, you can increase the mechanical properties, mechanical strength, but not always, because it levels up, the properties levels up beyond a molecular weight. So, there is no necessity of manufacturing or synthesizing very high molecular weight, because that will be difficult to process, is not it? If you take a very high molecular product, neither it will be you will be able to melt it, nor it will go into solution in a suitable solvent. So, to find out a suitable solvent or to find out a suitable temperature of processing is very difficult for the high molecular weight. So, you must leave it at some molecular weight, so that it can be easily processable. In other way, look, relations of polymer properties to molecular weight. You see here, you think of this impact properties, they think of melt viscosity. Melt viscosity increases in this fashion with molecular weight, whereas tensile strength, it increases in this fashion. Beyond certain threshold value, increase is not so much as is the case in lower molecular weight species. Look at the impact property, again it is like the tensile strength, impact property also levels up beyond certain molecular weight. Now, this is a range of molecular weight here, between this range of molecular weight, where you can have intermediate properties. This is known as commercial polymer range. Here the axis is not defined, So, the hypothetical range, hypothetical molecular weight range, where you can get adequate tensile properties, adequate impact properties, adequate processability. That means, you have to have a compromise, you have to achieve a compromise between the processing as well as the properties. If you want only very high molecular weight, but you won't be able to process it. If you cannot, if you are unable to process it, if you cannot make a product, that is useless. So, you have to make a suitable product. So, it should match with the processing machineries. That means, the machineries you have, say one extruder you have, or one your injection molding machine you have. So, if you get a polymer which is not which cannot give you the molded product or extruded pipes, then it is useless. So, for that, this is the range of molecular weight, which is known as commercial polymer range, where it processes well through the existing machineries, as well as it gives a balance of properties. Now, here you see some averages, number average molecular weight. Okay, thank you. এরকম করে থামিয়ে দিলে কি আর